Okay, so let's begin. Okay, so this is the main recap of what we did in the previous lecture. So we extended ideas from regular codes to irregular codes. The decoding extends in an almost trivial way. The analysis not quite in a trivial way, but it also extends. You have a density evolution formula. Okay, so that's the main idea. There is a density evolution formula which is parameterized by lambda of x rho of x. In terms of which gives you the probability that that there is an error in the message passed on a particular edge, on a random edge, so to speak, from one iteration to the other. So you can track this. Okay. So now you can again analyze the properties of this density evolution formula. So you remember we did some analysis and found whether it was monotonically decreasing in P, whether it was monotonically decreasing in PL minus 1. All those things will be true. Okay. But before we do all that, how do we reconcile this notion of average? Okay, so when you average over all these codes, right, how do we know that this formula is good for any particular code? Right? That's something that you have to answer. Okay, so what turns out, so you can prove something known as a concentration result. Concentration around average. Okay. What does the concentration around average mean? So if you take, for instance, the number of errors in a particular iteration, okay, number of errors that are there in the messages in a particular iteration across different codes from the same ensemble, it turns out it's concentrated around the average number of errors. Okay, so what does that mean when you say concentration around average? With probability close to 1, the density evolution formula will hold for any one graph that you pick from the ensemble. Okay, so that's what it means. Okay, I don't want to go into more technical details than that. Okay, basically once you show a concentration around average result, this implies DE formula holds for an individual graph or matrix. Okay, so this will it has some meaning in practice. That's what it means. Okay, even though you have, in your analysis you have averaged over all possible graphs, okay, and we are only computing the average. Okay, we have a concentration around the average result, which means the average is still meaningful for any one randomly chosen graph from the ensemble. It's like saying in a class the average marks was some say 60%, and then I also have a concentration around the average result which says with the number of people between 55 and 65 is maybe the fraction of people between 55 and 65 is, let's say, 0.98 or something. Then it means the average is very meaningful for every individual person. Okay, so if you ask a particular person's mark, you can give that mark correct to plus or minus 5 marks, right, which would be what? The average itself, you can say, and you would be right almost 98% of the time. Okay, so that's what this means, concentration around average. Okay, so it's a useful tool when you analyze a very complex algorithm. Okay, so when you analyze a complex algorithm in a particular situation, you may not be able to analyze it. What do? You average out all the situations, maybe the analysis becomes simpler. Okay, you will get some IID variables, some random variables will become IID when you average over all these things. Once you do that, the analysis is easy, but then the average may not be meaningful in practice. But if you have a concentration around average result, then that average analysis is still meaningful in practice. Okay, so it's a useful trick to remember in case in the future you are analyzing an algorithm as complicated as decoding, message passing decoding on huge graphs, for example. Okay, so the density evolution formula is meaningful and it works in practice. Okay, but remember the formula is a bit complex, right? So it's much more complex than the regular case. The regular case, at least you had just one expression. Here you have some summation over average over lambda I, then an average over rho j, then you have to take the powers individually and all that. So the analysis will be a little bit more, the expressions will be a little bit more cumbersome, but nevertheless many of the properties extend without any problem. Okay. So, what kind of properties are we looking at now in the DE formula? Okay. So, if you fix P or fix P, right, PL is a, well, fix P, F is monotonically decreasing in PL minus 1, you can show using some analysis. Same thing is true for PL minus 1 also. You fix PL minus 1, F will be monotonically decreasing in P. Okay. So, both of those will be true, and then you can also show the threshold phenomenon. Okay. There exists a P star which is maximum of P such that P infinity equals 0. Okay. So, it will be great if you have a closed form expression for P star, but usually you will not have a closed form expression for P star. So, you have to estimate it by numerical methods. Okay. So, what would be one numerical method of estimating it? So, you start with P equals 0, right, and see if what happens to P infinity. P infinity will clearly be 0, no problem. So, then you increase P by say 0.0001. Okay. So, how many ever precision you want? If you want a precision of 10 power minus 6, so increase it by 10 power minus 6. Okay. Then compute P infinity. How will you compute P infinity? You have to iteratively evaluate this formula till it goes to 0. Once it goes to 0, it will remain at 0, right. So, you evaluate this formula till it goes to 0, then see if P infinity is 0. If it is still 0, then you increment P again. Okay. So, you can numerically evaluate this to arbitrary precision. To some finite precision. That is good enough in practice. Okay. So, you won't need anything better than finite precision. So, you evaluate. Okay. So, now you can have your grand optimization program. What is your grand optimization program? You want to fix for a, so this is the optimization of degree distribution. Okay. Remember, what is this optimization for? It is for Gallagher A over BSC. Okay, that is very important, because the density evolution formula is for Gallagher A over BSC. Wherever you do density evolution, that is the exact optimization that you are doing. Okay. So, it is not for anything else. Okay. So, a code that you, a degree distribution that you get for Gallagher A over BSC might be very bad over some other channel under some other decoding. Okay. So, there is no guarantee that the same code will work over other things also. This is important. So, what will you do? The first thing to do is to fix a design rate R. Okay. This is version 1, I will call it version 1, I will also give you a version 2 which might be slightly different. Okay. You fix a design rate R. Okay. So, this in turn fixes what? Does not fix anything, but it provides constraints on Li and Ri, okay, possible degrees you can have. Okay. So, it is very common to also fix possible left and right degrees. Okay. Otherwise, your problem becomes really more complex and you may not really need to do that. And in fact, in most cases you will fix right degree to be constant or near constant or two possibilities. Two successive possibilities. Okay, that is what I mean by near constant. Okay. So, do not ask me why and all that. Okay. So, these are justified based on experience. Okay. People find that this is good enough for optimization. Okay. So, for a particular rate r, either you fix the right degree to be constant and fix left degrees. How you fix possible left degrees is, you will always fix the minimum to be 2, okay, and you will fix a maximum, okay, maximum say will be 10 or something, okay, so some maximum, and then you fix a few in between, few more in between. Okay. So, this is again once again why, because it works in practice. Okay. So, you even if you fix the maximum as some 10 or 20 or 30, you do not allow all the degrees from 2 to 20, okay, then your optimization will become so complex, your space becomes very big. Okay. So, you kind of have to minimize your space over which you are searching. So, these are ways of doing that without getting hurt in practice. Okay. So, that is the idea. Okay. So, once you do this, you will have several possible degree distributions. Okay. So, you can in fact find exhaustively all the degree distributions and try to search over them, but that is not usually done. Okay. So, usually what people do is some kind of a genetic algorithm. Okay, what are these genetic algorithms? There is this notion of differential, there is one algorithm called differential evolution. Okay. So, this is what is usually used. Okay. It also abbreviates as DE, but this is very different from density evolution. Okay. So, differential evolution, what they would do, I will describe very roughly. What you would do is, you will fix some capital N degree distributions, okay. So, you will first pick some N degree distributions at random. N is going to be large, think of it as at least 100, okay, 100,000, maybe huge number of random degree distributions which satisfy the rate constraint and these other constraints that I have put on it. Okay. You pick according to that, okay. And then what do? You compute N thresholds. Okay. How do you compute the N threshold? You have a numerical method for doing it, right. So, you compute the N thresholds. Okay. So, one among these will have the best threshold, right. So, you pick that best possible guy and then you evolve all your N minus 1 using the best possible one. Okay, it is like you have some genes, I mean the best possible guy has some good genes, you mix it with that guy kind of thing. So, it is genetic in that way. Okay. So, you do it roughly. So, how do you mix? One way to mix is to kind of join these two distributions in the space, then take some convex combination, etc. You combine the best distribution and every other candidate distribution to get a new distribution. That is the next evolution stage. Okay. You also keep the best degree distribution by itself, okay, and then you evolve everything else. And then what do? You have N evolved degree distributions for whom you once again compute thresholds, and among them there will be one more guy who is best, and then you evolve and evolve and evolve. Okay. There are no guarantees that you will get anything good. Okay. It is just that it works in practice in very complex optimization problems. Such methods work well. Okay. If you do some optimization courses later on, you can learn about many more genetic algorithms than this. Okay. So, when the problem becomes very complex and you do not have a very simple expression, you use these kind of methods. Okay. So, this is one way of doing it. When I can't really answer any questions about this because you have to implement it to see how it works. Okay. So, I have had students implement this and it works. Okay. You get good degree distributions out of this. Okay. This is the rough idea. Like I said, this is one way of doing it. There is also another way, okay, which is which gives you some rough linear programs, and these methods are also quite useful, and I am not going to exactly describe it, but this is how it works. Okay. So, what you would do is, I think you would fix a threshold, okay, a threshold, say some P0, let us say P star. Okay. So, you fix a threshold P star, some threshold probability, and then you maximize rate, the design rate over all lambda of x, rho of x such that threshold is greater than or equal to P star. Okay. So, this is kind of like a dual way of doing it. Okay. What did we do before? We fixed R and then we maximized P star over all lambda of x rho of x that satisfied the rate constraint. Now we are doing the other way. Okay. So you want all lambda of x rho of x, you want to consider only those which have threshold at least p star. Among those you try and maximize rate. Okay. The nice thing about doing this is, remember, rate is going to be 1 minus summation I Li by summation j r j. So what people do is usually they fix this part also. Okay. And there is a smart way of converting this constraint into a linear constraint, okay, into a sufficient linear constraint. Not even a sufficient, let us just say approximate linear constraint, some kind of a constraint which is linear, okay, in perturbing, etc. So this, it's a smart way to do this. So what is the advantage if you do all this? You basically get a linear program. Okay, so that's the big advantage when you do this other program. Okay, so the objective function itself is linearized by fixing the denominator, so it becomes linear in the Li's. Okay, and then you have to work with this constraint. Okay, so this is a difficult constraint to work with, right? How do I know the lambda of x and rho of x which give you a threshold greater than or equal to p star? I mean, that I don't know. Okay, but you can kind of look at the density evolution expression very closely and linearize it. Okay, there are ways of doing it, but like I said, it's only sufficient, not even sufficient. I think maybe even that is not proved. It's only approximate. Maybe it's just approximate. Some approximate linear constraints which guarantee that the threshold is likely to be greater than or equal to p star, and then you do a linear program to optimize it. Okay. So this is also complex, it is not as easy, and I think this is not as successful as the differential evolution method. Okay. Differential evolution I think is much more successful, but this is also pretty good, you get some good thresholds with this. Okay. For instance, what will happen is if you allow your left degrees to become very large, for instance thousands and 2000s and 3000 left degree, then the linear program works quite good. But if you want to get the best possible code for a left degree of 10 or 20, which is what is usual in practice, then differential evolution works much better. Okay, this approximation method does not work that good. Okay, that's a good rule of thumb to remember. All right. So that's it. I mean, there's not too much information in the in what I told you about the optimization. I mean, it's just something that you have to try. I mean, if you have to do it, you have to try. But until recently, Rudiger Urbanke was maintaining a website out of his homepage called LDPC opt. If you go and search for LDPC opt on Google, you will hit it, and he had a huge database of optimal degree distributions for different channels, different decoders, and different rates. Okay, it was there, but as it turns out, in the last few weeks, it's been down. So I don't know why, but I think it's going to come up again in a few more weeks or months or something. It's not going to happen immediately, but eventually I think it will come up. So once this comes up, then you don't have to do all these programming, right? So optimization you don't have to do. Okay, to know the best degree distribution, you just simply go to this web page and you get this. Okay, so this is maintained by Urbanke and his group, but hopefully they'll fix it and get it up and running. Okay. If it's not, then you are into trouble. Okay, I don't know if somebody has. If there is a mirror database, then that will be great, but I don't know if they have. I'm sorry. Maybe they are patenting. Patenting, yeah, maybe.
It's already patented.
So something has happened. Is it okay? Can I continue? Yeah. All right, so now this is really dramatic because okay, we have lights back again. Okay, so that's where I want to stop about Gallagher A. So by now, I think what you should have an impression of is some kind of rough idea of how to work with LDPC codes in practice. Okay, so how do you work if you want to design an LDPC code? Suppose you are faced with a channel. You start with a channel, let's say BSC of P, and the probability of error is given to you, channel transition probability of error is given to you. How will you design an LDPC code? If somebody says design an LDPC code, what will you do? What will you do? What will be the first step? Rate, okay. How do you decide the rate? Okay, suppose LDPC opt is available. Regular or irregular, okay. So let's say I want the best possible code in some sense. Okay. So suppose say LDPC opt is available, the database is available. Somebody has a database of what? All possible degree distributions, the best degree distributions for a particular threshold or best degree distribution for a particular rate, etc. Okay, then what will you do? You will go find lambda of x, rho of x such that what? Two conditions need to be satisfied. What are the two conditions? Threshold is greater than or equal to p, right? Because I know then the code has a good chance of working, and then what else is needed? I have to maximize rate, right? So that's a good choice. Okay, so you maximize rate. Okay, so these are the two constraints that you will try to satisfy when you look up this degree distribution. Okay, among all the degree distributions that give you a threshold at least p, which one has maximum rate? Okay, it is going to be irregular, right? It's not going to be regular. It's going to be an irregular code. And in practice, you might also have other constraints. I'll come to that later, but right now, let's just say we do this. Okay, and then what do? Are you done? Is this enough? What should you do? What's the next step? Okay, you fix a suitable n. Okay, n is going to be large enough. I mean, it has to be large. Fix n, and then construct a random parity check matrix from lambda of x, rho of x ensemble. Okay. So, I did not specify how to go from lambda of x, rho of x to L of x, R of x, it is possible, okay, and it is a 1-to-1 mapping. Given L of x, R of x, you can find a unique lambda of x, rho of x. Likewise, given a lambda of x, rho of x, you can find a unique L of x and R of x. Okay. So, once you have lambda of x, rho of x, you can convert to L of x, R of x, and then construct the parity check matrix randomly from the ensemble. Okay, and then what do? You are done, right? You can simply do Gallagher A if you like. Okay, so you do Gallagher A decoding. Okay, this is all for Gallagher A. Okay. Gallagher A decoding will work. Okay. Okay, but if you really want to use it, you cannot stop here, right? So you have to verify all the approximations and assumptions that you made in your analysis and choice. Okay, how will you do that? What's the only way of doing that? You have to simulate. Okay, so simulate and check definitely. Okay, so you have to simulate this and check. Okay, so some interesting things will happen when you simulate. Okay, so one of the important assumptions was n was infinite. Okay, in a practical system, you may not be able to have n infinite. Why will you not be able to have n infinite? Let us not say infinite, let us say a million. Why can't you have n million in many systems? Yeah, so there is problems, right? So there is a huge delay if you have n is 1 million, right? Your data is going to be maybe data rate is going to be 1 Mbps or something. Okay, by the time you process and finish decoding 1 million, some 10 million bits would have already come to you. You have to keep them somewhere. Where do you keep them? All these problems arise. So people don't tolerate such long block lengths in practice. Okay, maybe your block length can be at most, let's say 5,000. So that's a reasonable number today. Okay, 5,000 maybe is reasonable. Maybe 2,000, 3,000 is also reasonable. Somewhere around thousands maybe is reasonable for you. Then what will happen is when you actually simulate, suppose your p was let's say 0.04. Okay, and you thought maybe I can use a threshold which is 0.039. Okay, pick a code with threshold 0.041, let's say, slightly above, but your block length now is 2000. Then what will happen when you simulate? It will not be anywhere close to the performance that you want. You won't get 10 power minus 3 frame error rate or something near the probability of error 0.04. So then what should you do? You should back off a little bit more in the threshold. okay, 0.041 is not enough, so you go to 0.05 or something, okay, depending on your block length. Okay, so that process you have to iterate till all the approximations you made in your analysis make sense in practice, and that today, to the best of my knowledge, there is no theoretical way of doing it. Okay, so you have to do it by simulation. Okay, so you have to repeatedly do simulations and refine your degree distribution choice. Okay, so another thing that will happen is when you have n equals 2000, okay, right, you cannot have huge left degrees. Okay, so if your rate is half, n equals 2000 means 1000 is the maximum left degree you can have, right, you cannot have more than 1000. Okay, but even if it is 1000, even if it is even 100 with 2000, a 1000 by 2000 matrix with column degrees being 100, it is impossible to put it down so that you do not have length 4 cycles. So in the construction phase also you will have trouble, so you may not be able to let your left degree go very large. It can, for 2000 it can be maybe 10 or 20 or something, so it depends on how good your construction method is. Okay, so all those constraints will come in practice, but those are not very serious constraints, I mean you can get over them. So put some reasonable limits on these numbers. Maximum left degree, that is an important limit you have to look at. Okay, so maximum left degree you will look at, and finite block length effects. Okay, maximum left degree improves your construction, finite block length effects affects your simulation, and both these will affect your choice of lambda f rho of x. So you cannot just have these two constraints, you will have other practical constraints depending on how you have implemented the construction of the random parity check matrix from the ensemble, and how the simulation works for finite block length. Okay, both of these are very crucial. All right. So another thing, so several other things like this which will play a big role in practice. Okay, so one more thing which is very crucial when you have degree 2 bit nodes. Okay, so it turns out even though we have averaged over all possible degrees and we have an average formula for density evolution and everything is great, but in practice degree 2 bit nodes are very unreliable. Okay, if you have degree 2 bit nodes, okay, that bit is very much more likely to be in error when compared to other bit nodes. Okay, so that will happen in practice all the time. Okay, but another thing that will happen in practice all the time is unless you have degree 2 bit nodes, you will not have good thresholds. Okay, for a particular rate, if you do not have degree 2 bit nodes, you will not have good thresholds. So these are interesting things that many people do not have theoretical interpretations for. So you just know that this is true in practice, nobody knows why it has to be that way. Okay, there are some reasons you can think about, but it is not very clear. So there is like a balance you have to do, how many degree 2 nodes you want to put, that gives you good thresholds, but then threshold is good, but the bit node itself will have trouble in correcting. The degree 2 is only 2 check nodes. So what people do is the smart trick of making all degree 2 bit nodes as parity bits. Okay, so you will design your matrix such that you can make all the degree 2 bit nodes as parity bits. So what happens when you decode, even if the parity bits are in error, it does not matter, it will not violate anything else, your message bits will be correct, your CRC on the message bit will, or your cyclic redundancy check or something on your message part will validate, and you will be fine, you will proceed and you will be okay. Okay, so those are several, that is just one of the tricks. There are so many other tricks that you have to do in your construction to make things work very nicely. Okay, and that is all, several papers are there. If you search for LDPC, you will see thousands of papers in the past 15 years, and many methods are proposed to get over these kind of things. Okay, so what we are going to do next is stop with BSC and Gallagher A and move on to AWGN, BPSK, AWGN and soft decoding. Okay, so that is what I am going to do next. So this is a good time to ask me any questions on general ideas on irregular codes and what happens in practice, etc. Any questions? Nobody has any questions? Okay. So I mean, unless you program these things, you will not really learn all the intricacies and the tricks. Okay, and unless you have sufficient reason to program these things, you are not going to program these things also. So, but it is good to know this. I think it is an exciting and interesting problem to work with. Okay, so let us finish with this and move on to BPSK AWGN. Okay, and soft message passing decoding. Okay. So, many of the principles that we saw before will once again extend, but the fact that it is soft makes things a little bit more complicated. Okay. Many of the things that were very simple in Gallagher A will not be so simple anymore, okay, but nevertheless the essential ideas will nicely extend without any problem. Okay. So, you do not have to worry about it. So, if you have a good feel for what is happening in Gallagher A, you will also understand what is happening in the soft message passing decoding, but there are some intricacies which will complicate matters a little bit. Okay. So, for one, we were passing just one bit back and forth. Now, what will we be passing? We will be passing technically real numbers or more than one bit, definitely infinite precision, we will be passing a lot of bits. Okay. So, analysis becomes a little bit more involved. Other than that, it's pretty much a straightforward extension, works very much like Gallagher A in spirit. Okay. All right, so let us do the setup of the problem. So, you have a code word C from an, let us say, so I will once again stick to regular codes to start with, and then the extensions to irregular also will follow in a very obvious way. Okay. So, you have a code word C from a WCWR regular LDPC code. Okay. So, this is first, this goes through BPSK, and BPSK as before will be 0 going to +1 and 1 going to -1. I have a symbol vector R to which Gaussian noise, which is distributed 0 mean sigma square IID gets added, and you get a received vector R, and you want to run a decoder on this to produce, let us say, a CCAP. Okay, this is the general idea, and this R is going to be R1, R2, Rn, and what will be important or what is called soft information is usually the LLR or the scalar LLR small l sub I, which will be 2 Ri by sigma square. And what is this? This is the probability that Ci equals 0 given Ri divided by log. Okay, I forgot the log. Log is important. Probability that Ci equal to 1 given Ri. What is the base of this logarithm? Let me ask this question. E. Okay, it's log base E. Yeah, because it's e power 2 Ri base. Just asked a quick question. Okay. All right. So, this is the real input to the decoder. Input to the decoder is R1 through Rn, but we usually use the LLR as the input. Okay. So, what will happen in soft message passing decoding is, remember we were passing estimates of a bit in Gallagher A. Okay. Here we will be passing LLRs for the particular bit. Okay. So, in soft message passing, messages will be messages on edges will be estimates of LLR of bit corresponding to the bit node connected to the edge. Okay. So, that will be the first significant difference between the hard decision decoder and the soft decision decoder. We will not be passing just the bit, okay. We will be passing back and forth estimates of LLR. I am saying estimates because it will not be accurate. Okay. So, ideally we would like to pass the accurate LLRs, but we will not keep track of accurate LLRs, some estimate, some local estimate based on what we know, we will pass estimates of LLR. Okay. So, this is the most important and critical change. Okay. Other than that, the principle is the same. Okay. You have some channel information that is received and loaded onto the bit nodes. What is the channel information now? It is not just one bit, it is the scalar LLR. Okay. In the first iteration, what will the bit nodes do? they will pass that scalar LLR to all the check nodes that are connected to it. Okay. And what will the check nodes do? They will receive LLR from all the bits that they are connected to and pass updated LLRs back. Okay. Right. You will also maintain the extrinsic nature of the messages. How will you maintain extrinsic nature? The same thing will not be used when the check node passes back. Then what will you do at the bit node again? You will collect all the new LLRs that are coming in, then use the extrinsic, send back extrinsic to all these guys. Okay. That is the essential principle. Okay. So, let me write down how it works. I will write down the description of the decoder and then we will think about analyzing it, etc. Okay. So, this is how it works. In iteration 1, okay, the bit node, let us say the ith bit node which received Ri will send, remember I am looking at regular LDPC codes. So, how many check nodes will I have? WC check nodes. Okay. So, this will simply pass Li to all the check nodes that are connected to it. Okay. And what will the check nodes do in the first iteration? Okay. So, let me write that down. Okay. So, this check node would have received L2 through LWR. Okay. It will also have received L1, but it will not use it, and it has to compute now what I have been calling as U1, okay, just U1, okay. So, be U11. Okay. So, what is this U11 supposed to be? Okay. So, these are bits 1 to WR. Okay. I am just numbering them as 1 to WR for convenience. Okay. So, this U11 is going to be LLR of bit 1 estimated using L2, L3, so on till LWR. Okay. We already know how to do this. I will quickly write down the formula, you will see what I mean. Okay. Remember the bit node knows C1 to be equal to what? C2 XOR C3 XOR so on till CWR. Okay. And the individual log likelihood ratios are known, L2, L3, LWR. Okay. How will you compute the extrinsic log likelihood ratio for C1 now? The 2 tan hyperbolic formula is there. Okay. So, usually you can compute U11 to be 2 tan hyperbolic inverse. Is there an inverse? Inverse of tan hyperbolic L2 by 2 tan hyperbolic L3 by 2 so on till tan hyperbolic LWR over 2. Okay. So, that is the formula, it is as simple as that. Okay. What will I do for U12? What will this be? What is U12? It is the message that is going in that edge. Oh, U21, I am sorry. Oops. Okay. Instead of L2, you will put L1, that is it. So, you will have 2 tan hyperbolic inverse tan hyperbolic L1 by 2 tan hyperbolic L3 by 2 so on till tan hyperbolic LWR by 2. That is it, and so on. Okay, I do not have to write what the other messages are, that is what will happen. Okay. So, what is going to happen in iteration 2? That is quite important. Iteration 2, in a particular bit node you have Ri of course, okay, and then you now have prior information coming in from other check nodes. Okay. So, maybe I number this 1 to WC. What comes in from here is U1, 2, okay, again I am numbering for convenience, it is not to, I will not be doing it consistently, okay, and then this also will be coming in U1, 1, and I want to send out V2, 1. Okay. How will I do this? Okay. So, what is happening at the bit node? Bit node is received an estimate of the LLR from the channel, okay, which is Li, right, and then now it is receiving WC other estimates from each of the check nodes that it is connected to, okay, and as far as the bit node is concerned, all these estimates are independent estimates. Okay. So, now based on all that the bit node knows, it has to send back some estimate to the first check node which is extrinsic to that check node. What all is extrinsic to that check node? This guy is extrinsic, this guy is extrinsic, this guy is extrinsic, and all these are LLRs and they are all independent. So, what can I do? Simply add them all up and send it to bit node, that is all. So, you send V12 to be Li, of course Li will always be there, plus U21 plus U31 plus so on till UWC1. What will you let V1, V22 to be? Same Li plus U11, U31 plus so on till UWC1 and so on. Okay. So, once you understood the principles of Gallagher A, this is also very similar. Okay. So, you are not doing anything different except that the updates are now LLRs. So, the formulas will come from probability. Okay. Once you know the assumptions, the formulas will directly come, but in Gallagher A we had one artificial way of creating this V11, right. It was quite artificial, I mean it was just some ad hoc kind of method. If everything agrees, then you make it B, otherwise you do not make it R. Okay. So, here it is a method that will come from probability itself. Once you decide it is LLR, right, there will be a certain way to compute it, there is no other way to do it. Probabilities, once you assume independence, probability calculations will tell you the answer. As the LLR, they all add and they go to the other node. Is that okay? Okay. So, now I can formalize both these iterations and write down iteration L. There will be two steps, one from the bit node to the check nodes. Okay. U2 L minus 1, UWC L minus 1, and what goes out V1 L, this maybe is some, okay, I should say Li here because I am using L also for the iteration, hopefully it is not confusing to you. And so on for other, for okay. So, okay, similar for the other things. Then what do you do at the check node? V2L, VWRL, I want to send back U1L. Now, how do you compute U1L? 2 tan hyperbolic inverse V2L by 2 tan hyperbolic be L WR by 2 and so on for U2L, etc. Okay. So, that is it, as simple as that. Okay. And there are all efficient ways of implementing it, which I have not gone into great detail here. For instance, so you never do these multiplications actually. So, what you will do is you can write this formula as, so you bring this 2 down here, becomes u1 by 2, then take tan hyperbolic on both sides, you get tan hyperbolic of u1L by 2 equals product of several tan hyperbolics, then you do logarithms on both sides. So, you get log tan hyperbolic of u1L equals sum of log tan hyperbolic of all these things. So, it turns out log tan hyperbolic in absolute value you can always invert very easily, okay, because they are taking log, no. So, you have taken absolute value, the inverse is itself, okay. So, all you need is one nonlinear function which is log tan hyperbolic, okay, and then you can write u1L as f of summation of several f's, okay. So, there is a very simple way of implementing this which I am not going into here, okay, but it is possible to implement this in a very simple fashion. Same here with the left hand side also, you do not have to keep doing this summation several times, you add up everything and then subtract one after the other. Similar thing you can do on the check node also, like you did on the check node you can do on the bit node. Okay. So, all of this can be implemented in a very nice and simple way, but essentially this is the idea. Okay. So, this is soft message passing decoding in BPSK AWGN, and this is in fact the major selling point for LDPC codes. So, today the way technology is, you can get soft information from the channel on every bit, okay, and you want to have an efficient way of using the soft information. We saw that this MAP decoders were what, theoretically okay, but there is no easy way of efficiently implementing them. Okay. So, that bottleneck is nicely solved by this kind of a decoder. So, you see it is easy to use the soft information, you are iteratively improving it one iteration after the other, okay. You are using more and more code words from your parity check matrix and XORs of code words from the parity check matrix in a way that is specified locally by the Tanner graph. Okay. So, you go on the computation graph and that is how it is specified, you do it smartly using that and then it works really well. Okay. None of the operations are that complex, and in fact in practice even if you do like 5 or 10 iterations, 5 iterations even, you will get very good performance. Okay. So, you get a good great coding gain, etc. All right. So, that is the soft message passing decoding, that is it. It is as simple as that, nothing more to do, anybody can implement this, and in fact you can write like a 35-36 line MATLAB program for it, you do not need anything more than that. It is very easy to write code for something like this, okay, and you will get good performance. Okay. So, the next important step is density evolution. It is fine enough that I have an algorithm, I can of course use regular codes for a particular design rate, I can use 3,6 if I want rate half and I will get some performance, but once again you will notice that there will be a gap between the capacity at a particular rate and the thresholds that are obtained by regular codes. So, you have to do irregular codes. So, when you do that you need a good density evolution. Okay. So, now density evolution is much more complicated here. Why is it complicated here? So, the messages passed are not bits anymore. So, you can't just say probability of a bit, what should you track instead? The PDF of the random variable which denotes the message. Okay. So, it becomes more complicated because of that fact. So, you are not tracking just one probability, you are tracking an entire PDF. Of course, you can't track the entire PDF in practice numerically. So, you will approximate it, you will bin it, you will track a long enough discrete PDF, and that will give you a density evolution algorithm. Okay. So, we will stop here for today and we will see how to do density evolution in the next lecture. Okay. So,